Assalamualaikum warahmatullahi wabarakatuh and a very good day. We are Group 2 from Section M01 will present the report for our lab, Experiment 5, which is Pelton Turbine. My name is Muhammad Iqbal Afif bin Shamsuddin and my number is MA19031. For the introduction, a hydraulic turbine in which one or more water jets impact tangentially onto buckets positioned around a wheel is known as a paddle wheel. The force generated by the jet collision produces a torque which causes the wheel to rotate, generating power. Despite the simplicity of the concept, some very large high-efficiency devices have been constructed. It's not uncommon to see power output of more than 100 MW and efficiency of approximately 95%. The output of small laboratory model, on the other hand, could be as low as a few watts, because losses in bearings and windage are proportionally much larger than in a large, powerful turbine. The efficiency will be substantially lower. A source of water is required for the Pelton wheel to function. If the water head and flow rate are known, it is simple to determine the ideal size of wheels to use. How quickly it should rotate for maximum efficiency, and how much power it will be generated. Using the non-fixed head, the velocity in the jet may be approximate. From the non-flow rate, the diameter of the jet may be calculated. In relation to the jet size, a stable wheel diameter can be determined. Normally, the wheel will have a diameter of 10 times that of the jet. The ideal rotational speed can then be chosen, with the buckets rotating at around half of the speed of the jet. The speed and cross-sectional area of the jet can be used to compute the power delivered and the ratio of the wheel efficiency, which can be predicted by referring to the known performance of existing machine of equivalent size and output. The power developed by the paddle wheel will be less than this. The size and speed of the paddle wheel obtained in this manner may be unfeasible or uneconomical depending on the head and flow rate available. Other types of turbine fortunately are available to fit a wide range of needs. When the available head is high but the flow rate is low, the paddle wheel is frequently chosen. This is pattern wheel layout. The purpose of this experiment is to investigate the paddle wheel's operating principle. We will examine the features at constant head in this laboratory, which will include the link between torque and speed, efficiency as a function of speed, flow rate as a function of speed, and hydraulic and mechanical power as a function of speed. The main goal of this lab is to measure a pattern wheel turbine's power output and compare it to the theoretical power output. Another goal of this lab is to test the loss of turbine scaling.
Assalamualaikum, my name is Rajina Zura, MA1906. Now I am going to explain about the theory of this experiment. First of all, we need to calculate the flow rate by using the data that we taken from the experiment. Flow rate and the time taken. And then we need to calculate the turbine power. As we can see, turbine power is equal to 2 pi nt over 60, where n is speed, t is torque, p is power. Torque here we need to calculate. Torque, this is the torque measured by the two spring balances in this experiment. As we can see from the picture, the torque is the radius of the drum multiplied by the force, whereas the total force is the difference between the readings. From the picture, due to the direction of rotation, the right hand balance will give a larger reading than the left hand balance. So for simplicity, torque is equal to F1 minus F2 multiplied with RB. Where F1 is load reading on the spring balance, right hand balance. F2 is load reading on the spring balance, left hand balance. While RB is brake wheel radius, which is a constant value here, 0.025 meter. And then to calculate power and efficiency by using these two formula. Hydraulic power is a function of the volumetric flow and fall height, okay, where P power hydraulic is equal to V flow rate, H fall height, rho, which is the value is 1000 kilogram per meter cube, and then G is gravitational force. This is 9.81 meter per second square. Okay, and then the turbine efficiency defined as the ratio of output power to hydraulic power. Okay, that's all.
Assalamualaikum and a very good day. My name is Siti Nur Inshira, M01 I would like to continue the presentation by presenting the method and procedures for this lab experiment. For the experiment setup, firstly, we have to double check all the connections to make sure that all connections are secured so that no water will be spilled. Before initiating the investigation, we also have to make certain that the braking device is not loaded. Next, we need to identify the flow rate from the hydraulic bench, and after that, use the information obtained for the Pelton turbine computations. The nut cap is used to rotate the nozzle valve axially. The nozzle placement is checked from a scale on the lid. The jet is centered by the adjuster sleeve using a WAF-10 wrench, ensuring that the water is evenly distributed on both sides of the blade. The equipment and materials needed for this lab activity are the Pelton turbine HM150.19 demonstration Pelton turbine and hydraulic bench HM150. Next, follow the following procedure to obtain the required flow rate. Firstly, switch on the pump, then fix the timer to 0. After that, shut the valve at the base of the volumetric tank. Patiently wait till the water level reach 10 liters and start the watch simultaneously. 60 seconds is a decent measuring duration. Next step is to halt the stopwatch once the water has arrived at 20 to 30 liters volume. Following that, jot down the measured time and the high water level inside the tank. After that, use the table given in the lab sheet and finally deduct the flow rate by using a formula provided.
Good day everyone, my name is Jing San and my ID is M01 I'm here to talk about the chapter 4, which is results, graph and discussion for the LAB5. Let's begin with the experiment part 1, which is the characteristic curve. The formula applied is the volume flow rate, net head, and the torque. And this is the power turbine, the power output, and the power input. And we calculate for the efficiency, which is the power output divided by the power input. So this is the sample calculation where we calculate for the first data and the efficiency also. After that, we table it into a table, which is here. You can see with the rotational speed and with the torque, output, power input, and the efficiency. And then we use this data to plot the graph. This is the graph of torque vs the rotational speed. And we can depict that the torque is decreased when the rotational speed increase. Yes, you can see the graph is going down. And for the power output and vs the rotation speed, when the power output, when the rotational speed increase, the power output also decrease. And same goes to the efficiency. When the rotational speed increase, the efficiency also decrease. And we proceed to the part 2, which is the power curve. And we have the rotation speed same, and we got so the power output, and we calculate for the torque. And we can see that the maximum power output is at 470 RPM, which is 2.08. We can plot the curve, and we can see from the curve that the rotation, the power output increase with the rotational speed, and then reach maximum, and then decrease eventually. So that's all from me. Thank you.
Question 1. Explain the graph of torque vs RPM.
I am going to answer the question. As you can see, this is the graph for torque versus rotational speed. When the rotational speed is increased, the torque of the turbine shaft is decreased. I would like to ask the second question. Could you please explain about the graph for power outputs versus RPM?
It's me again, Vijing-san. I'm here to answer the question 2, which is the power output of turbine shaft is increased from 130 rpm to 470 rpm. Then it started to decrease while the rotational speed increased. Hi, it's me. I'm here to ask my teammate, which is the question 3. What is the maximum torque produced?
For the answer question 3, the maximum torque produced is 0.0750 Nm at the rotational speed of 601 rpm.
And I'm also going to ask the question 4. What is the maximum power output from shaft with the constant nozzle?
For the answer question 4, the maximum power output from shaft with constant nozzle is 4.7202 watt at the rotational speed of 601 rpm. I would like to ask the question 5. What is the efficiency of the turbine?
Okay, answering the questions 5. The average efficiency of the turbine is 29.44%. The highest efficiency is 45.83% at the rotational speed of 601 rpm, while the lowest efficiency is 10.18% at the rotational speed of 801 rpm. Okay, for the
question 6, what is the maximum power of the turbine can produce?
uh, question 6, what is the maximum power the turbine can produce? Okay, the maximum power the turbine can produce is 3.08 watts at the rotational speed 407 rpm. Okay, my question is question 7. Which nozzle position produce the lowest power?
Answer 7. The quarter position of the nozzle generates the lowest power. This occurs as a result of the pressure being higher in one place than in another. Lower power can be produced with a higher rotating speed.
Assalamualaikum and good day. My name is Daniel bin Abdullah and my number ID is MA1057. So today I will make the conclusion about our experiment. In conclusion, the experiment attained a reasonable level of accuracy. Furthermore, the data were useful in determining the properties of the machine. As a result, more of the time was a success. The result also made it feasible to create a more precise visual representation of the working foundation, including the turbine attributes. The purpose of the experiment, which was to determine how the spinning speed of the pattern wheel changed over time, has been achieved according to the data.